Today we're going to see how we find differential equations for mechanical and electrical systems, and what is the process on to begin this modeling by using the differential equation first, which is in fact what we know as the block diagram method, because a block diagram is a physical representation of the is a mathematical representation of the differential equations in graphical form. Okay, so what I would like to do is to review this a little bit in here, how we uh, how we do this differential equations for both kinds of systems. We have on the left the electrical system, the one have on the right the mechanical system. The reason I would like to do it this way is because I want you to see the similarities on how we analyze each one of the systems. Because when you think about it, the situation is that we need to do systems that are in both energy domains. But first of all, we're going to see that uh, certain things are very similar, and there are elements on one system and the other that have about the same kind of functions, but in different energy domains. So we'll explore this system in parallel, both on the block diagram as well as on the bond graph method. So first, because we have the equations in there, we're going to go with the block diagram method. And so we'll begin now by looking at this slide in here and seeing that we have a differential equation in here. Differential equation has been modified, and we have the differential equation on the bottom, and even further modified to make it to write it in this format down here. On the mechanical side, we have the system itself here. We have done a free body diagram of the system over here, and the differential equation has been derived following and applying Newton's law. What you may notice is that the format of this equation on the right hand side is like the format of this one on the left hand side. So how can that be if both of them are in different energy domains? And it can be because the elements that perform the electrical resistance, for example, they operate in the electrical domain, while the damper here that provides the resistance occupies in the mechanical domain. But this is suggesting that this format is suggesting that, for example, this spring is like this capacitor here on the electrical system, and this inductor is like the mass over here. Granted that they're not the same because they have the different units, these equations. But there are some similarities that I think are worth pointing out. So what we're going to do is let's go here to my OneNote and look at the electrical system first on the left hand side, and we are going to proceed with finding the differential equations for this. Let me augment the graph a little bit to put the physical parameters. This is a C element. This one here is an R element that we have. The one on the right hand side, this is a voltage source in here. Yes, and this other one is an inductor. Yeah, you have the, you have in here the current inside. Just gonna put it I for the current. Yeah. So this is the description of our electrical system. So what we're gonna do is let's just apply the Kirchhoff's laws to the circuit. So remember I like writing steps. So we could put the steps here on the electrical side, and let's just maybe I'll just do it here. See, like here. Okay, I'm gonna say let's just call it the steps. What did I just do? I moved it over when I shouldn't. Okay, here. Steps. Okay, the first step would be, I will say, recognize the elements we have. Yeah, so we have done that. So it's got an R element, a C element that has an inductor in there. Then the second thing we're going to do is to write the equations according to Kirchhoff's laws. So this is the situation here that we need to apply those laws right now. So let me I'll leave a little space so that we still have time, some place to write, but I am going to begin over here, maybe just right here, say, okay, so is Kirchhoff's law, it says that the summation of the voltages, you see, around a loop are equal to 0. Or you could say the source voltage is equal to the voltage drops of each one. You know, voltage of R plus voltage of C plus voltage of L. So if this is true, you will have you will have that voltage equals to I times R plus 1 over C, the integral of I dt, like this, and then plus L times di dt. See? So this is the voltage on the resistor, this is the voltage of the C element, and this is the voltage of the inductor. Yeah. So you see, in here we have this differential equation, but it is written in a mixed format because you see it has integration and it has differentiation, all this stuff. And we cannot use it this way. We need to have all as a differential equation. So what we need to do to remember such a thing is uh, we are going to replace the equivalent of the current is dq dt. See, so if this is true, therefore you have that voltage is equal to dq dt times R plus 1 over C and then you have to say the integral of dq dt like this dt, right? Plus L times d square q dt squared. So I think, yeah, we put it in terms of the q variable. So let's reduce this. So in here you can say you can rewrite this equation in terms of the highest derivative. You can say that L times d squared q dt squared is equal to v minus r times dq dt plus, this would be no, plus minus 1 over c times q. See? So what we need in this case is, as a third step after we apply the Newton's law, you could say express the differential equations in second order form, meaning do this substitution of variables that I is equal to q dt, and then we have it in second order differential equation. And then I'm going to say is, we will say organize, organize in terms of the highest derivative. So the highest derivative is this, the term L is LD squared Q dq dt squared. So at this point, what we're going to do is represent this equation in graphical form. In order to do that, we need to start with the summation point. So let's just put that as step number 4. Represent the equations in equivalent block diagrams. What does it mean? It means that in here you're going to have a summation point, and we are going to represent that in a graphical form. So let's go over here, and we are going to do this. What we are saying is that in the summation scheme of things, the output of that sum is L times dq dt. Okay, so in here you see you have this b, so that's, yeah, b. So we have We have checked this term. Of course, we have done something with that. And now these other two, they are two negative ones that we need to add to this block diagram. So one of those is going to be like kx type element. Okay, so we're gonna write the other two in here. This be minus 1 over c times q and minus r times dq dt. See, this again with minus signs, plus minus minus. This is the very basic um, graph so that we can actually draw the rest of it. So in here, what we need to do is first we divide by L, then you have that this is the QDT. And then you have this scope to.
Is the DQDT a second order?
No, no, it's just, oh, the one at the top is this one. Yeah, this one is. So, but you see, this has R times dQdt. You have this dQdt, and then you multiply by R. And the second one is so this is 1 over S. I think we have a little bit of correction to make in here. We need to integrate this thing twice. So in here, we're going to integrate once now, and then 1 over S the second time. So this would be dq dt, and this one in here. See? So this would be q. This is going to measure it, but I think just to be on the safe side, we're going to erase this. Oh, the erased it more than I wanted. Okay, so you see we go completing the block diagram now. Yeah. This is Q, so it calls to pick Q from here. Put it through the gain of, I believe, is 1 over C. Completing it here.
You have to move the R.
Huh?
They are moving over to past the integrated.
I see. Very good observation. We have just one line that needs a little bit of a correction. That's this one right here. And yeah. Okay, so we are ready to put into the Simulink now. And that's what we should do next. And then we should try the mechanical system later on. This is the idea, is this in here. Okay. So we'll reduce it to the point that we will we could just see it on Simulink. So we're gonna leave it here for now, and then we're gonna go and start MATLAB and go to Simulink. All right. Okay, so we have to wait for a moment until MATLAB comes up, and what we're going to do is to get the um, description of this block diagram into the Simulink. So we have to wait for a little bit until we get the MATLAB prompt. At the prompt, we enter the word Simulink, and MATLAB will actually run the Simulink section, which is a MATLAB. It's a tool from MATLAB. So MATLAB has a bunch of added tools to calculation, but in here for this purpose, we want a file that can load things ahead of time, so it won't be so slow. So a little bit of a waiting here until MATLAB comes up. Yeah. Okay, so now it came up. We are at the prompt and we're gonna type Simulink. Oops, no. Yeah, we type Simulink, and so now what it's gonna do is it's gonna give us a workspace in there, uh, some section of the disk that we can write and do exercises. There we go. Simulink came up and gave us this. If you click on new file, and then we can transfer everything. Yeah, there we go. We're gonna transfer the elements that we need. We need like 3 of these. Okay, so we still need some others from here. We need a scope. We need scope allows us to measure things. Okay, we need the summation point. Where is the summation point?
On one end,
So,
right there. Right there.
Right here. And I believe that's about right. So what we need to do is on this one, you see, we're gonna rename it the way we want it. Yeah. So here we have, oh, we have to put one positive and two negatives. So positive, plus, and minus, minus. Mhm. That allows us to better distribution. And then you have this ones.
you need,
We need the integrators. That's the, I know there was something that we're still missing here. This one. We need two of these guys. These ones, we need to flip them over. We do a control I. Yeah. Yeah. So in here you have this. Oh, we still need to fix this. And then we're gonna put this one connected to this. This one didn't do quite a good connection. So we need to put some values into this. This is going to be our voltage. We're gonna put the use the letters. So this is 1 over was 1 over L, right? Okay. And then let's just make it a little bigger so we notice the way it is. This is the B variable. And we have what happened here. We need one last connection to this. It didn't quite do it. If it is red, it's not connected correctly. Yeah, there you go. So if we had some numbers and values in here, we just run the simulation. So we're gonna use this in here and put the numbers in here. The numbers would be something like L equals to 1. What else do we have? K. Let's see. What else do we have? We have L, you need to define, and R, and 1 over C, and B. So now we have transferred this into this. So it's time for us to give it some values and see if it actually works. So I am gonna put this. So where's the MATLAB prompt? Right here. So L is equal to 1, R is equal to 2. Then we have L is equal to, see,
Oh, you already defined out.
they are
So
what?
you're missing C. You already defined L. You're missing C.
We need to define C. I think it's lowercase c. This is going to be 1 over 40 like this.
And B.
Okay, and then B.
B.
B is, this is going to be a 5.
But it's not that. It's B. 'Cause it's
What?
The voltage.
Huh?
It's the voltage. So B.
It's what?
B.
B.
Oh, the voltage also we need. The voltage equals to 10, let's say. Yeah, with all these values in, we can go in here and then run the simulation.
You're missing the variable.
Am I?
In the lower game. Yeah, one.
Which one?
Oh, you're missing
Something is, okay. What very L we have?
C. 1 over C.
Oh, this one is 1 over C, like this. Okay. So let's try again.
The other triangle is R.
Yeah, we do this, then everything is cool, and it's actually it's correct. So this is the simulation for the electrical system. So we have gone through the steps. Let's just review the steps in here to make sure that we have it all in one place, what we did. So represent the equations in equivalent block diagrams. Then you could say run simulation and Simulink. Yeah, Simulink. Okay, so this is this is for the electrical side, and for the mechanical side we can do the same thing, following a process to do the differential equations, but in this case, Newton's laws are not going to apply. So in this case, we are going to apply Newton's laws, and I would say, okay, we're gonna go to step number 1. This is going to be make a free body diagram of applied forces. Then apply Newton's law. Say 2, apply Newton's law. Apply Newton's law to the masses. Just very briefly, here says apply Newton's law. That means summation of forces equals to to the rate of change of momentum. Okay, so that's what we're gonna do next. We will go on ahead and apply this, and then we're gonna go and see here summation of the forces. So in here we have the free body diagram. I'm going to give some room so we can write over there. You have this okay, so having this block diagram allows us to apply the summation of forces equal mass times acceleration, right? So, and this would be F minus K times X. Speed times X is equal to mx double dot, like this. Huh?
This brain is not going the other way?
No, because you see what happens is we put it X this way, right? So when we move this, the spring is going to oppose the motion. So once we have it this way, it's pretty much the same process. We create a block diagram. This is part of it. This is F. This is mx double dot. And in here, you see you have these two negative terms. And then on the left hand side, minus k times x, and over here, b times x dot.
Is 1 over n?
Huh?
1 over n?
We still haven't done that yet. Right now, all I'm trying to do is to get you to relate this I would like you to relate this method, the simple, I mean the way we transform the differential equation into the graphical form with the 1 over m, and I here with bx dot double dot. You integrate once, and with bx dot. We need to integrate it once more, and then we have the scope. Alright? But you see, well, what you have in here, in a very similar way than the mechanical system, and here you have this feedback is for B, and then you have this other one over here. This would be the feedback for 1 over C. Okay, in this case. Like that, see? Once you have this block diagram, putting it into Simulink is the same as we did with the other system. So you have seen here, just to summarize, you have a set of steps for the electrical system, a set of steps for the mechanical system. Here, I would say we could just add here, transform the C3, transform the equations into block diagrams. And then finally, perform the simulation. So that way you have seen how we go about doing. In this case, we didn't have to put it in terms of the highest derivative because it was already there. And then we translate this into the Simulink file, and it will work the same as the other.